Welcome to today's session on the first SSbD trainings, which is for safe and sustainable by design training. So today we will focus on lignin safety in bio-based food packaging. So we will explore the safety assessment in the SSbD framework. We will explore some practical application and data related to our BIO-SUSHY project. So practical data. So you will see example and you can make question. My name is Michele Ponzelli. I am from AXIA Innovation. And we are the partner dedicated to dissemination and exploitation in the BIO-SUSHY project. And I have the pleasure today to moderate this session. Before we start, I want to give you some housekeeping rule. So before you ask, I'm sure that this question usually comes. All slides and recording will be available. So the recording and the slides will be sent to you possibly within the week. So you will receive both of them. And you can check it also later on. But I think today you have the opportunity to make question, especially we have a 15 minutes dedicated question and answer session where I think that's the important that you participate in the live. So for a question, indeed, you can either raise your hand and we allow you to speak. So we allow your microphone and your camera, or you can just type the question in the chat. Okay, so as I said, we will be until 11:30 around. We will have an introduction of BIO-SUSHY, and then we will get into the SSbD part. So first we will start with more, let's say, theoretical part, and then we will have the practical part with the Q&A. I would like to first give you a brief, like 3 minutes overview of the BIO-SUSHY project. What's BIO-SUSHY about? So in BIO-SUSHY, we are aiming to replace PFAS from coatings. So PFAS, as you can see, are per and polyfluorinated alkyl substances. So are substances that have this carbon-fluorine bond, which is very strong and cannot degrade in the environment naturally. That's why they're also known as forever chemicals. So it's tackling issues. And in BIO-SUSHY, we aim at the source. So we want to develop coatings that doesn't contain these PFAS. PFAS are very useful. PFAS is especially oil and water repellent properties, and they are used in everyday products, from pans to food packaging, as today in glass. So they have a lot of application. So the objective of BIO-SUSHY in tackle this environmental challenge is to develop 3 bio-based coating. So we have one organic bio-based powder, which will be used for the food packaging. And then we have 2 hybrid sol gel coating, which will also be applied for textile and cosmetic glass packaging. Indeed, BIO-SUSHY is based on 3 pillars. So we have, as I said, the coating development, so the part related to the development of this novel coating, and the and their final validation, because in BIO-SUSHY we have 3 validation cases. So in the food packaging, textile, and glass cosmetic packaging. Then we have all the part on modeling, where we apply QSAR modeling to anticipate the toxicity of certain chemical compounds. And also we have also another set of computational tool in helping us also in the SSbD framework, which we will see today some steps that we carry out, that we perform. So BIO-SUSHY is distinguished itself from others because we have the validation in 3 case studies. We have, through a biomembrane sensor that you will also see today, the possibility to evaluate and assess the toxicity of a coating with a biomembrane sensor. And then we have all the part on the application from the early stage on SSbD and the standardization. So we want also to influence policies and get standardization and certification of our solution. So BIO-SUSHY impacts are here, you can see here. So we aim to provide business opportunity to European Union SMEs. We are boosting the European Union research, development and innovation. And of course, we are reducing the amount of PFAS in the environment, so we are preventing their release. And we have a dedicated work package on social acceptance, so how the different stakeholders will accept this novel coating, and also what are their willingness to pay for such novel bio-based coating. So here you can see a bit all the value chain and the different steps involved in BIO-SUSHY, ranging from modeling and computational tool, the scaling up, the characterization, until the validation. The team, we are 15 partners, 14 of them from the EU. You can see here from research center, social, small and medium enterprises. We have 1 university from United Kingdom and 1 national association from Spain. And the coordinator is Materia Nova, located in Belgium. So I will conclude just saying that you can stay in touch with us. We have a semester newsletter. We have every 4 months, we also have blog articles, so you can get some of insight also on what we're doing from the blog article. So you can download our poster, our presentation from the website, and you can check also our videos. So feel free to connect with us. Okay, so we can start the first session of today's training on SSbD framework and steps, which will last around 15 minutes. Our next speaker has expertise in safety assessment, so on how to implement SSbD practice from the early stage development to the final product. She has a degree in biotechnology and 3 master degrees in food biotechnology, bioinformatics, and packaging technology. Our next speaker is a project manager of the ITENE Process and Product Safety Unit, and she brings experience from various international projects related to SSbD. So welcome to Pau. You are very welcome to share your screen.
Thank you. Just a second. Just let me know when you're able to see my screen.
It's perfect. We can see full screen.
Perfect. So I will explain a little bit about the SSbD framework and the steps. Oye, vale, no pegamos bien. Ah, ya. The European Green Deal, with the European Green Deal, the European Commission aims to transform the European Union's economy for a more sustainable future, focusing on climate, biodiversity, circularity, as well as better protecting human health and the environment as part of an ambitious approach to tackle pollution from all sources and to move towards a zero pollution economy for a toxic-free environment. To achieve these objectives, the Chemical Strategy for Sustainability calls for the transition to a safe and sustainable by design approach for chemicals. The SSbD Framework has been published by the European Commission and JRC, and we can say that the SSbD approach aims to obtain functional materials while avoiding damage to human health and the environment as a consequence of the process, production, use or disposal of these products or materials. This is possible by the identification and reduction of the hazards or potential impacts at an early phase of the innovation process. As mentioned before, these approaches address the safety and sustainability of the material or product along whole life cycle. The methodology proposed by the SSbD Framework is a 5-step methodology that for each step we assign a score for each step that allow us to determine if the material or product under development could be safer and more sustainable than current alternatives. So the framework focuses in two aspects: safety and sustainability. In the case of the safety, by carrying out a hazard assessment of new materials developed for human and environmental health. And to do that, we can use methods based on IATAs, NAMs, experimental as in vitro tests of bioassays, in silico methods, and finally, if we don't have the option, using bibliographic results, and also with the process hazard assessment. And in the case of sustainability, doing an assessment of the environmental impacts generated by products and processes through their life cycle and socioeconomic impacts. So what we understand by SSbD is an approach that focuses on providing a functional materials or products while avoiding damage to human health or the environment as a consequence of their fabrication process, use or disposal. In essence, the SSbD approach aims to identifying and minimizing, at an early phase of the innovation process, the impacts concerning safety and sustainability, minimizing the environmental footprint, in particular regarding the climate change and resources use, and protecting ecosystem and biodiversity, taking a life cycle perspective. So the SSbD approach addresses the safety and sustainability of the material or chemical or products and the associated process along the whole life cycle, including all the steps of the research and development phase: production, use, recycling, and disposal. The strategy proposed is based on 3 main pillars. The first pillar is a safe and sustainable material or product by design. By this strategy aims to minimize possible hazards coming from the material or the substance's nature and its hazardous properties, as well as sustainability issues of the design material or product, but always maintaining the function. The second pillar is safe and sustainable production, and is based on the safe and sustainable production in order to ensure industrial safety, in particular occupational, environmental, and process safety aspects. This pillar should also ensure the sustainability processes during the production of materials or products, minimizing emissions and resource consumptions, and optimizing waste management. And the last pillar is in relation to the safe and sustainable use and end of life of the product. By minimizing the The aim here is to ensure that the materials or products are designed in a way that the hazard and the use of the resources are minimized during their use and disposal or recycling phases, supporting these principles in the circular economy. So the methodology that we follow in a SSbD project is the following. First, we need to define an SSbD criteria for each step. Then we need to obtain the information about the chemicals or products or process that are carried out during the project, and to obtain all the available information. And then with all of this, we are able to do the steps that are proposed in the SSbD framework. In BIO-SUSHY, the three first steps are carried out by ITENE, supported by University of Leeds. The step 4 is carried out by Materia Nova, and the last step by Woodca Plus. In this workshop, we are only focusing on the first 3 steps. So how can we apply the first step? So the first step, for the step 1, 4 levels are defined from level 0 to level 3 that will allow us or the assessor to arrange the specific chemical based on these levels, and further to integrate these results of the hazard-based evaluation to the overall SSbD assessment. So as we can see in this slide, we have the level 0, that if we categorize some chemical in this category, it indicates that it's prioritized for substitution. The level 1 substituted as far as possible, level 2 flagged for a review and eventually reduce toxic effects, and the level 3 is that this chemical pass all the safety criteria that we have defined. So in BIO-SUSHY, what we do is first we ask to the partners to give us a list with the chemicals that they are using, and then we see if there is a regulation regarding these chemicals, as for example REACH and CLP regulations, to see if there is a hazard sentence that in the safety data sheet that it's not included. Then we do the assessment based on with the safety data sheet, and with all this assessment, we can propose actions to be taken in the project. The step 2, 5 levels are currently defined that will allow us to rank the production and processing related risk levels, and further to integrate these results of the hazard-based evaluation to the overall SSbD assessment. As this step is based on the process, we can see that in the table that there are columns based on the hazards from release behavior and process-related hazards. As I said before, 5 levels are defined. The level 0 and level 1 you need to prioritize for modification or substitution. Level 2 is flagged for review and eventually reduce toxic effects. And the level 3, the chemicals or materials that pass the safety criteria in step 2 as well as level 4. And what we do is, as in the previous step, we first do the assessment of the chemicals by REACH and CLP regulation, then with the safety data sheet, and then we do a occupational assessment, while we ask to the companies to complete a questionnaire to be able to identify which scenarios are critical to be able to do or an in silico assessment, or going to the company to do an occupational monitoring. With all this information, we are able to propose actions to reduce the impacts that could be generated by the production. And finally, the step 3. For the step 3, For the three levels are currently defined, from level 0 to level 2, that will allow us to rank the human health and the environmental impact of the final application of the product, and further to integrate these results of the hazard-based evaluation to the overall SSbD assessment. The level 0 is the action need to be taken. Level 1 is that flag it for a review and eventually reduce the ecotoxic effects. And the last level, level 2, that chemicals or materials that pass all safety criteria. So in the project, what we do is an evaluation of the migration of these chemicals and materials into the product contained in the packaging, for example, the evaluation of the migration of chemicals and materials into the environment. The computational models can also be used to predict some important endpoints. Assess the migration of the chemicals and materials that may reach humans during the end-life phase, and also assess the migration of chemicals and materials that may be released to the environment during the end-of-life phase. With all of this, we also propose actions to reduce the impact to the environmental and human health. And from my side, that's all.
Thank you very much, Paolo, for illustrating us also the first 3 steps. So giving us a brief overview on the whole SSbD framework, what is it about, and the first 3 steps that ITENE is working on in BIO-SUSHY. Now we will move to next session on lignin types. So we will see different lignin types, full assessment and example. Our next speaker has experience in thermoplastic-based material and formulation development, which is very interesting for the bio-based solution economy practices that some of the participants are interested in. Ivana has a background in organic chemistry and polymer engineering. Right now, she's an international project manager at the bio-based composites and processes team of Wood K+ in Austria. And she has a significant experience in polymer processing technologies, and she also worked at the Johannes Kepler University. The floor is yours.
All fine. Thanks a lot for this nice introduction. So yes, for this first BIO-SUSHY training today, basically my speech is all about to introduce more technical part of our value chain. Let me just move to the full screen. I hope you can see it now.
Yes.
Good. So yeah, as I said, basically my speech is more technical one, and I would like briefly to show you the technical part of the food packaging value chain, and basically what is the role of Wood K+ and how we combine the different expertise with our partners on SSbD Framework. So just first to explain briefly the role of Wood K+ in BIO-SUSHY project. As already mentioned before, we are part of Work Package 2, where we do develop different formulations, particularly focusing on novel coatings to replace PFAS. And Wood K+ is basically contributing to the formulation development for thermoplastic powder coatings. Our material development is linked to the food packaging value chain, and we have here involved actively an end user, Ecosema, from Italy in this value chain. So as said before, our role is development and validation of different organic coating materials. The technology that stands in the background is spray coating applications on paper, but not only on paper. Basically, our activities are also focusing in the near future on cellulosic substrates for food packaging. And as mentioned, definitely, since this is one of the SSbD projects, we are working very closely in close cooperation with SSbD partners from BIO-SUSHY to address different safety and sustainability aspects that are today crucial for any R&D material development. Then just briefly on the food packaging case study, we basically identified at the early beginning of this project last year, our targets, as said before, PFAS, to replace PFAS in a paper coatings, and we started working with different bioplastic materials, polyhydroxyalkanoates, different types. And besides that one, we also selected the polybutylene succinic acid, another thermoplastic matrix, and there is a goal to combine that with natural polymers like lignin. So why we would like to do like that? Because in terms of the performances, water repellency is something that is crucial here, because our food packaging case study is focusing on a fast food packaging for takeaway food, which consumes a lot of basically waste today. Therefore, one of the goals is also to provide some more sustainable solutions when it comes to end of life. So water repellency is there crucial on first functionality of such packaging, and the second one is basically grease resistance. And of course, in any of our technical assessment, we are following the standard ISO testing for the food packaging. What is also very important in respect to the sustainability, bio-based content at least should be 80% in our formulations. We have to look also later on the food contact tests according to the EU regulations. We have to be non-toxic, safer compared to the currently used materials following SSbD approach. As mentioned, spray coating is here the technology to apply the materials on a paper. The target is 100 micrometer thickness. Here we basically observe film formation, ultra thin coating layer on a paper, which is followed by the hot press and thermoforming to obtain the food tray. So on this slide, basically, I want to show you briefly different steps how we apply such organic coatings on a paper. Of course, we start with the state-of-the-art technology compounding, mixing different components. Then it is followed by the second step, which is grinding, very common also in the preparation of powder coatings. And then the third step is basically spray coating to apply such formulations on a paper. And that step is basically followed by hot pressing, where we basically, it's film formation on a paper by increasing the temperature according to the material that is being used as a coating. On the next slide, since today our training is basically focusing on lignin safety and showing its potential to be applied as a coating material, I would like to mention in our activity, formulation development, we investigate lignin from two different aspects, to use it as a single component on a paper, but also as an additive. So what has been done at the early beginning of the project, we use the craft lignin from UPM. BioPIVA is the grade because it has to be modified, and it was being modified by our partner from France, Sychemia, by alkoxysilane with long alkyl chains to chemically modified that can provide water repellency. Because due to the nature, lignin tendency is more to be polar than non-polar. Therefore, it has to be modified to provide certain water repellency. And on the right-hand side, you can see two different examples of the modified and not modified lignin coated on a paper substrate. And this is just a bit on the chemistry of lignin. Today, I do not go too much to the details, but just that you can see that we performed some functionalization of lignin and that basically improved the water repellency once lignin was being applied alone as a coating material on a paper. The results, which are, as I mentioned before, are always crucial to look on that. Later on, we have a kit rating, which is basically providing us information on the grease resistance. And here you can see basically the comparison of different thermoplastic materials being used alone on a paper, like PBS, PHBV, and PHBH, another type of PHA, and its comparison to the modified lignin and not modified one. From those results on water repellency and kit rating, we can see that basically once UPM BioPIVA lignin was not modified, it showed some moderate water repellency, which was the same for the PHBH thermoplastic polymer. But once lignin was modified, we basically observed water repellency, which is our target in here. Which is a bit different, quite different once we look on the grease resistant. At the end of the day, as a next step in the project, we decided to combine the functionalities of different thermoplastic matrices with modified lignin. And I would be very happy in the case someone from our audience today has some more concrete questions to answer today and to go to a bit more details. So this is basically all what I wish to show you today. I would like to also thank all our partners that are cooperating with us very closely in this project. And I'm looking forward to the next presentation when we talk about more on the safety assessment of lignin. I stop sharing.
Thank you very much, Ivana. It was interesting to see how Bootcamp Plus is passing from the formulation and all the steps of the development, and also to see some data related to what we can achieve in terms of oil, grease, and water repellency. Next part, it's related on safety assessment before we go into the break. And then we will have also the practical application session. We actually have a question. I think we have a minute, we can take it. Probably it's for you, Ivana. So Ula is asking, what was the melting point of modified lignin in heat pressing powder coating?
Yes, that's a good question. It was, I believe, around 80 degrees, but let me check because that's another table that I do not show. I believe I didn't show on this screen because, of course, it might be a bit different due to the modified groups. But in hot press, it was not longer than 100 degrees that we obtain a very good uniformity of the film on the paper, and at the end of the day, of course, those functionalities that are crucial in our food packaging. I want also to mention that, that this hydrophobic level sometimes also can be tuned in the case of lignin, and this is basically that we are evaluating further in this project using basically different commercially available lignin, modified lignins. But since this talk today is mainly on the safety assessment, we do not show everything, but probably in the near future that you can learn more on that.
So next session, as I mentioned, it's on the safety assessment. We will have again Paul with Ashi. So they will share this session. So our also next speaker, she will be focused on membrane interaction and coating material. Ashi's research is on electrochemical biomembrane sensor, and she earned a PhD from University of Leeds in electroanalytical chemistry, and she worked indeed on coating release studies, so directly applied to what we are doing in BIO-SUSHY. She has also a background in teaching and research at the University of Engineering and Technology in Pakistan. So welcome to Paul again, and also Ashi. The floor is yours.
Thank you. I will share again. Um, um, okay. So how can we evaluate the safety? In BIO-SUSHY, we can use computational tools. Well, in BIO-SUSHY and all projects, we can use computational tools and also in vitro tests. When the information is not available, computational tools can also be used to predict some important endpoints needed to perform the assessment following the SSbD framework. The structure-activity relationship methods are based on the idea that the biological activity or chemical property of a molecule can be related to its chemical structure. When quantified, this relationship is known as QSAR, quantitative structure-activity relationship. QSAR is a mathematical relationship which correlates measurable and calculable descriptors to specific biological, pharmacological, toxicological activities in terms of an equation. The OECD principles for QSAR validation are a definite endpoint, an ambiguous algorithm, a defined domain of applicability, appropriate measures of a goodness of a fit, robustness, and predictivity, and a mechanistic interpretation if it is possible. In the next slide, I try to include some computational tools that are already available, but I will not go deeply because I think that it will take a lot of time. So for the step one, we can use, for example, Vega, Danish user database, and Janus. It is important that, for example, if we are in the case of Lignin, for example, we can use some of them, but we need to ensure that, for example, the applicability domain, because in some of these models, the applicability domain for lignin it's not adequate. For the step two, we can use ProScale, SETOC, Stoffen Manager, ART, and Integra. And finally, for the step three, we can use Merlin Expo, Live Vermeer, and Integra. And now I give floor to. I'm sorry, I forgot one slide. So the steps to be followed is, first of all, we need to select the relevant endpoints to be predicted, and also select which models are the most relevant. Then collect the input data needed, for example, the smell of the chemical, and then we have to run the model. With the results, we need to evaluate the predictions and remove unreliable results. And if we don't have multiple models available for the same endpoint, we have our final output. But if not, we have to combine the selected predictions to obtain a final output. And then I give the floor to Ashley.
Thank you, Michele, for the introduction. And as Michele has introduced you all to the BIO-SUSHY project, and Ivana has introduced to the materials that we have chosen for the safety assessment today, I would like to mention our role at University of Leeds in safety assessment of lignin and coated lignin paper in context to the BIO-SUSHY project. So our role is mainly to screen different coating materials and coatings, resultant coatings for their membrane disruption assessment at various stages of their development, starting right from the material selection to the synthesis of formulation, and finally the resultant coatings by performing release studies on these coatings. So in my today's talk, I'll be discussing the biomembrane sensor that we are using for screening of lignin and modified lignin, and flow release accelerator that we are using for release studies of the lignin and modified lignin coated paper, and dosing challenge that we faced during the lignin screening because of its poor water solubility, and biomembrane sensor output for lignin and leachate screening, application of the safe and sustainable by design framework, and some of the achievements and future directions. So the membrane disruption assessment of coating materials and the resultant coatings, they are performed using innovative mini floor release accelerator, which is coupled with the biomembrane sensor. And in the first step of the membrane disruption assessment, coating materials, they are screened using a high throughput screening technology, which is based on a biomembrane sensing platform. This biomembrane sensor is very sensitive and responsive to the presence of small amount of different materials ranging from large size polymers to the small size nanoparticles, nanoclusters, from toxins to the useful therapeutic agents like peptides and drugs and different coating materials and formulations. In the second step, release studies, they are performed on the coatings using floor release accelerator. And during the release studies, these coatings, they are exposed to the reagents under different conditions of temperature, pH, and reagent composition, simulating the natural environment. The reagents which are generated after the exposure to coating and having any leached out coating constituents, we call them leachate. Leachate from the release accelerator, they are then subjected to the biomembrane sensor for membrane disruptions caused by the leached amount, and this signal towards further tuning and moderation of the coating formulation following the SSbD approach. So there is the biomembrane sensor diagrammatic representation of the biomembrane sensor that we are using for the screening. And this is based on an electrochemical system and is made up of various electrical and fluidic components. This biomembrane sensor, it consists of a self-organized lipid layer on the surface of the mercury electrode, and mercury is used in a very tiny micro amounts in the form of thin film on the platinum surface. So this lipid-supported electrode is then assembled in, it is used as a working electrode, and it is assembled into a flow cell. The flow cell is made up of aluminum and has a few acrylic and silicone layers having the different purposes like locator, flow channel, and sealing. So in addition to this working electrode, there are two more electrodes, counter and the reference electrodes. They are assembled into the flow cell, and all these electrodes, they are connected to the potentiostat here. And the flow cell has an inlet for the incoming fluid and an outlet for the waste material. And the inlet is further connected to the system of syringe pumps. I don't know if you can see my cursor. Okay, so this is the system of syringe pumps that is connected to the flow cell, and from the lipid syringe, lipid is injected into the flow cell to assemble a new lipid layer on the electrode surface. And from the sample which is under investigation, it is injected at a flow rate of 1 ml per minute into the flow cell to see its interaction with the membrane, lipid membrane. And after the exposure to the sample, lipid layer is equilibrated. It's allowed to equilibrate for about 30 seconds. And therefore, the total assay, it takes about 1.5 minutes to complete. From the buffer syringe, buffer is injected into the flow cell to clean the system after every assay at a flow rate of 4 ml per minute, and to get it ready for assembling a new layer. Every assay is performed on a newly constructed lipid layer on the electrode surface, and all the assays, they are done in triplicate. So from here, the potentiostat is used to apply a negatively increasing potential at a very high scan rate of 40 volts per second using a technique called rapid cyclic voltammetry. And data is presented in the form of the current is actually monitored from this potentiostat after application of the potential. And this data is acquired using data acquisition device, and it is then been presented in the form of the rapid cyclic voltammogram, which we call as the RCV plots. So here is the RCV scan, which is a very characteristic frame of the very good compact and impervious lipid layer on the surface of the electrode. So it has different distinct regions which correspond to the different phase transitions. For example, the constant current region and the two sharp current peaks. So these regions, they have been investigated in detail and are reported to be associated with the underlying phase transitions. For example, in the constant current region, the lipid layer is impervious and very well packed. And the first current peak, it corresponds to the electrolyte penetration, followed by the second current peak, which indicates the reorientation of lipid molecule, resulting in the formation of lipid bilayer in equilibrium with the electrolyte. So in the presence of membrane active materials, different changes, they occur in the RCV plot and are interpreted in terms of their interactions with the membrane. For example, an increase in the constant current region, it indicates the penetration of the membrane active materials into the hydrophobic part of the membrane due to the changes in dielectric, and any peak suppression or shift in peak along the potential axis may be associated with either the adsorption of the molecules at the surface or replacing the lipid molecules. So here I have presented some of the RCV plots, which are used as a negative and positive control for the biomembrane sensor and for the release accelerator. So in this RCV plot, we can see that there is not any change either in the constant current region or in the peaks, both of the peaks. So this is a very good negative control and from the leachate which is obtained from the copper substrate. Whereas in the bottom RCV plot, we can see that both of the peaks, they are expressed completely. So this here we can see that the leachate which we obtained from the cuprinol coated copper substrate has completely damaged the membrane. Cuprinol, we know we have it's a paint, wood paint, fungicidal paint. So, and we know it's toxic. So that's why we have used this as a positive control. Here, I have presented some of the results from the previous study, which is done before this project to validate the biomembrane output against the cytotoxicity assays. In this study, the cytotoxic measurements, they performed using colchicine, methyl methane sulfonate, and chlorpromazine on the two different cell lines, THP1 and CACO2 cells. And the outcome of the biomembrane sensor is related to the cytotoxicity measurements on these two cell lines. So we can see here that the biomembrane sensor output, it correlates very well with both of these CACO2 cell and THP1 cell culture studies. And we can also see that from the concentration axis, that the biomembrane sensor output is more than 10 times sensitive as compared to the cell culture in vitro cytotoxicity assessments. Yeah. So here, we know that the lignin is very poorly water soluble. Therefore, dosing of lignin to the biomembrane sensor in aqueous medium, it was really a great challenge to us, and we deal with it by making the heterogeneous water dispersions of lignin and by ultrasonication, and then the supernatants, they were subjected to the biomembrane sensor to see the interactions of the solubilized lignin with the biomembrane. And the same supernatants, they were also analyzed on the HPLC for the measurement of the actual amount of lignin, which is in solubilized form in the supernatant. So So here we can see that the amount of solubilized lignin is relatively much lower than the amount of lignin that is used to make these dispersions. So from here, we can see from the very complicated structure of the lignin, it's a complex biopolymer. And in solubilized form, it can exist in different oligomers in the form of lignin phenols. But we are using HPLC to quantitatively measure all those oligomers obviously, the HPLC chromatogram, they do not tell us. They do not tell us about the qualitative data, like what type of oligomers they are present. For that, we have a separate plan to analyze the leachates and any lignin solutions on the LC-MS. But for now, we are using the HPLC to quantitatively measure the whole bunch of lignin oligomers present in the supernatant and the liquid and the lignin solution, supernatant solutions. Yeah, for the membrane disruption assessments of the lignin and the functionalized lignin, RCV plots, they were recorded by subjecting the different concentrations of these lignin to the assembled lipid layer in the electrochemical flow cell. And then the percentage peak expression, it is measured as a matrix from the RCV plots recorded before and after each lignin exposure assay. This percentage peak suppression is the direct estimation of the membrane disruption, which is caused by the membrane active materials or lignin in this case. Percentage peak suppression is then plotted against these. Yeah, so this percentage peak suppression is plotted against the concentration in the form of calibration curves, and this concentration is obviously taken from the HPLC analysis, and calibration curves, they are presented here for both the lignin and the functionalized lignin. To increase the solubility of lignin, different concentration of sodium hydroxides, they were also used in additional set of experiments, and peak suppressions, they were calculated, and calibration curves, they were required. So here in these calibration curves, I have compared the peak suppression and hence the membrane interactions caused by the lignin and functionalized lignin in the absence and presence of sodium hydroxide. So we can see that the lignin interactions, it increased with an increase in concentration, both in the presence and in the absence of sodium hydroxide. In the top plot, the data is fitted to the Langmuir adsorption isotherm, and we got very good fit. So interaction of both the lignins, uncoated lignin and the functionalized coated lignin with the biomembrane sensor, it follows the Langmuir behavior, where the interactions of the lignin with the biomembrane sensor increased with the increase in concentration of the lignin until the saturation point is reached. So in case of the unfunctionalized lignin here, the presence of sodium hydroxide, in the presence of sodium hydroxide, the membrane interactions, they increase significantly compared to that of the membrane interaction in the absence of sodium hydroxide. Sodium hydroxide, it has been reported to depolymerize the lignin to the lignin derivatives. So sodium hydroxide here has not only enhanced the solubility of the lignin, but also it has hydrolyzed the lignin molecules to the different lignin derivatives, oligomers, which presumably have acted more strongly with the biomembrane sensor compared to the lignin itself in the polymeric form. And if for functionalized lignin, here we can see that there is a difference in the membrane activity of the functionalized lignin in the presence and in the absence of sodium hydroxide, but the difference is not it's not great. So we can here we can assume that the lignin surface in case of functionalized lignin, it has the silane grafting, as Ivana has shown in her presentation. It has so this silane grafting on the surface of lignin, it has protected the lignin polymer from depolymerization and the hydrolysis, which may account for relatively small difference in the membrane interactions of the functionalized and the unfunctionalized lignin under similar conditions. In the bottom plots, the data is fitted to the conventional dose response models, where the interactions, they increase with the amount of the dose of the lignin. And again, we got the good fits. So here, here I have presented I have compared actually the reactivity of the unfunctionalized lignin with the functionalized lignin under different amounts of sodium hydroxide used. Again, the top plots, they are the Langmuir fitting, and the bottom plots, they show the dose response fitting. And here we can see that the peak suppressions, they are relatively higher in case of functionalized lignin compared to the unfunctionalized lignin in the absence of sodium hydroxide. So keeping in view that all of the conditions, they are same, we are not using any sodium hydroxide here in this case. So the only difference is the presence of the silane functionality on the surface of the lignin, which presumably has contributed to the overall enhanced interaction of the functionalized lignin as compared to the unfunctionalized lignin. While in the presence of a small amount of sodium hydroxide, the lignin, uncoated lignin, it depolymerize or hydrolyze, and the interactions increase with an increase in concentration. But still they are less interactions as compared to the unfunctionalized lignin. Further increasing the amount of sodium hydroxide, the interactions, there is not any significant difference in the interaction of functionalized and unfunctionalized lignin. So the interactions in the unfunctionalized lignin, because of the depolymerized product, they reach almost to the same extent as the silane protected lignin. So the similar kind of data can also be seen in the dose response plots. So here I have shown the diagrammatic representation of the coating release accelerator that we are using for the membrane, for the release studies. And this is the top-down view of the flow release accelerator. So here we can see that in the flow release accelerator, the coatings, they are assembled into these flow cells. And the reagent from the reagent bottle is pumped with the help of the diaphragm pump and with the help of selector valve to these flow cells. These flow cells, they have a silicon mat heater at the back of all of these flow cells, which helps to increase the temperature of the coating and the reagent in contact with these coating to certain desired amount. This silicon heater can increase the temperature up to about 300, but we can't go beyond about 80 degrees because of the temperature sensitivity of the different components of this flow cell. But we can raise the temperature up to 80 degrees successfully using with these flow cells. And then from these flow cells, the reagent is collected with the help of selector valve in the collection bottles. And then the leachates, they are sent to the biomembrane sensor for analysis of the biomembrane disruption effect caused by the leached materials, and to the HPLC for determining the amount of the lignin and unfunctionalized lignin which is leached into the leachate. Flow release accelerator can be used in direct as well as in recirculation mode, depending upon the amount, depending upon this, for example, the case application. For example, recirculation mode, it accounts for the shear force, and it is used in case of the release studies which are performed on the textile applications. Similarly, the flow release studies, they can also be performed using the static cell this is used depending upon the nature of the substrate. Some of the substrate, they cannot work well, they don't work well in the flow manner. So then we also use the static cell for those release studies. Sorry. Yeah, so here I have presented some of the data from the released lignin, and these are the RCV plots of the leachates from the lignin and functionalized lignin coated paper acquired at two different temperature, 20 and 60 centigrade. So from the peak suppression versus substrate plot, we can see that the peak suppression is almost it's zero for the control, which is the phosphate saline buffer that we are using, indicating the absence of any type of impurities in the system. So the system is very clean, and it can be used for for assessment of membrane disruption caused by the leachates. So from the reference paper, which is the uncoated paper, we can see that the peak suppressions, they are very insignificant, less than 10%. It can be used as a very good control for the coated lignin coated papers. From the functionalized coated paper, the leachate, which it gives the peak suppression of about 0 at 20 centigrade, but there is some peak suppression at 60 centigrade. But in contrast, the leachate from the uncoated or UPM coated lignin, we can see that there is significant peak suppression at both the temperature, 20 and 60 centigrade. So when these leachates, they were analyzed using the HPLC, the amounts of the lignin in the HPLC, we can see that functionalized lignin is leached to about 0 centigrade, to the 0 milligram per mil at 20 centigrade, and to a very little 0.073 milligram per mil at 60. But in contrast, the uncoated lignin has leached considerably at both the temperatures. Here we have shown that the SSB technology it worked very well for the assessment of membrane disruptions caused by the lignin leached into the leachate. So from our studies, we can conclude that lignin is released from the coated papers, and the lignin is biomembrane active. And this biomembrane activity, it relates, it depends on the type of the lignin, whether it is uncoated or unfunctionalized or defunctionalized. So we have successfully shown the use of SSbD technology for feedback to modify the material design. And here I have just shown some of the results from the previous work already published, indicating the cytotoxicity of the lignin, both directly by cytotoxicity assessment and indirectly by the cell viability studies. So from our data, we can say that lignin is released lignin is released. So we have successfully applied the SSbD approach for online signaling to moderate the coating formulation. And we can also see that there is successful modification of the lignin surface, which resulted in the slow release of the functionalized lignin, which could be further reduced by either modifying the functionality on the surface of lignin, or by compounding the lignin with some other thermoplastic polymers to reduce the amount leached. And finally, I would like to thank my professor, supervisor Andrew Nelson, Nick Cupper, and Janine Will, and Josh for their cooperation in this project, and all the BIO-SUSHY consortium, especially Ivana, Christoph, Pau, Javier, and Aud for collaborating in this project.
In BIO-SUSHY, to ensure the safety, ITENE performed a risk assessment involving in vitro toxicological studies based on OECD protocols using cell lines, as for example, A549 9 cell lines derived from alveolar wall epithelial cells, HACAT cell lines derived from adult skin keratinocytes, and KCO2 cell lines from colorectal epithelium, simulating the main routes of entry into the human body: inhalation, contact, dermal, and oral, to evaluate the cytotoxicity and genotoxicity. And as you can see in the next slide, in this one, from cytotoxicity, we have obtained that the lignin modifier not produce any cytotoxicity. And as well as in the case of genotoxicity, that as we can see in these figures, any genotoxicity is observed. Also, we can evaluate the thermal irritation effects by carrying out an MTT test using the reconstructed human epidermal model. And with the media of this MTT, we can also do an inflammatory test to evaluate if there is reaction from interleukin 6, 8, and 18. With all these tests, we are able to know if the chemical produces irritation and sensibilization. And finally, in BIO-SUSHY, we also perform occupational monitoring. This is important for the step 2 because we need to ensure the safety of the workers. So to do that, the first step is a virtual or computational assessment where we define the occupational exposure scenarios through qualitative assessment using control banding tool NanoSafeD. With this, we are able to define the specific scenarios that are most interesting to do an on-site monitoring, and also we can also provide recommendations to each scenario. And once we have the identification of the most interesting scenario to perform an study on site, we do an experimental monitoring campaign using occupational devices as CPC, OPS. Depends of the scenario. We will select which device is the most interesting. And this is an example of which scenario could be. For example, the first scenario, the company is the chemical formulating company, and the process that we will evaluate is the modification of the lignin. The second scenario, for example, the formulation of different compounds to produce the coating. And the third scenario could be the application of the coating on the food packaging. With these results, we do we are able to say to the companies which actions need to be taken in order to reduce the impact or the effects to the workers. And I think that that's all from this part. Michele?
Yes, thank you. It was pretty dense and insightful presentation from both of you. We learned a lot, especially on the functionalized lignin, how it performs, and regarding the occupational monitoring. So I think now we can go, we have the break. We are pretty on time. We can meet back at 10:50, and during the practical application session, we will see more practical examples. So we will analyze some chemical compound, and then we were ample Q&A. I already saw some questions coming in. So we will have also around 15 minutes for questions. So there will be ample space for that. So now we will analyze, and we will have a practical example, a practical application session. I think we have 2 chemical compounds, and we will go through their identification and through the first 3 steps of the SSbD, so how it's performed in the BIO-SUSHY. So in this session, we have all our speakers, which will be jointly giving this presentation. So
for this practical application, we have prepared a case study that it's the use of a new chemical compound named E to be used during the lignin functionalization instead of the chemical compound B which is currently used. So if we were in BIO-SUSHY, the first that we have done would be review the information from ECA and the CLP, then obtain the safety data sheet from supplier. Then we would compare both following the SSbD framework, and finally, with the final score, decide which one is better. So here again, the same slide where we would like to point out that it is important to do the assessment of the chemicals by the REACH and CLP regulation if they are inside these regulations, then perform the assessment of the chemicals used in particular by the safety data sheet. And with that, we can propose actions. And if we wouldn't have any of this information, we should do the toxicological test and the biomembrane sensor that we have showed before. So for the chemical compound A, for the REACH and CLP regulation, it's not classified. Then with the safety data sheet that the supplier provides, we saw that there is 3 hazard sentences. The 314, 318, and 332. If as I said before, if we don't have any information, we should confirm if they are toxic or not with chemical test or by in silico models. But as we have this safety data sheet, we are able to classify that following the SSbD framework. And we can see that all the sentences related to human health are not included in category A and B. So we would classify them in group C, that it's level 2. For the environmental hazard and physical, there isn't any hazard sentences. So it's classified as a group D, that is level 3. And as always, the more restrictive level is the dominant. So we said that for this chemical, is classified as level 2, flagged for a review and eventually reduced toxic effects. And for the chemical compound B, we saw that it's under REACH and CLP regulation, and we can see the hazard sentences 314. And also that it's an endocrine disruption for human health and environment from category 2. With that, and also with information provided by the safety data sheet, that as it shows in the slide, there is 1, 2, 3, 4, 5 hazard sentences, 4 related to the human health and 1 for the physical hazards. So with all this information and following the SSbD framework, we can classify this chemical for the human health hazard and environmental hazards as a group B, level 1, because there is the endocrine disruptions and also, no, because there is the endocrine disruptions. And regarding the physical hazard, we would classify it as a group C, level 2. And as I mentioned before, the more restrictive level is the dominance. So we would classify for the step 1 this chemical as a level 1, substitute it as far as possible. So if we do the SSbD score for the step 1, we can see that for the chemical A, sorry, because I don't know why the figure is not, it doesn't appear, but however, anyway, for the step 1, for the chemical A, the score is 0.89, and for the chemical B, it's 0.444. So if for the step 1, we would choose the chemical A. However, we need to go until the last step in order to see which is the best. For the case study 2, for the step 2, we proceed as before. First, we need to see the REACH and CLP regulations, then the safety data sheet, then we need to classify the process risk, and then estimate the exposure of the workers to potential hazard materials or chemical. With all this information, we would be able to say which action should be taken. So for the chemical A, we can classify as proceed. For acute human health hazards, the level is 2, as well as for chronic human health hazards. That it means that flagged for review and eventually reduced toxic effect. For physical properties, as there isn't any hazard and following the SSbD framework, the level should be 4. For the hazard from release behavior, the same. But as we asked for the company, and we saw that for the process-related hazards, the level should be 3. So for the final classification of this compound in the step 2, we would say that it's level 2. In the case of the assessment of the chemical B, is more complex. The classification for the hazard sentences H314, 318, and 302 in the acute human health is level 2. However, the hazard sentences 331 is classified as level 1. So the more restrictive is assigned. For chronic human health, the level assigned is level 2. And for the physical properties, the hazard sentences listed is also level 2. Then from the hazards from release behavior, we saw that the vapor pressure is 70 hectopascals, I think that was. So it's defined as level 1. And then for the process-related hazards, the level is 4. So at the end, this chemical B would be classified as level 1. So if we compare the scores obtained for the chemical A, the score for the step 2 could be 0.75, and for the chemical B, 0.5. So again, for this step, we would choose the chemical A. And finally, for the cases for the step 3, we should do the evaluation of the migration of chemicals and materials into the product container, also evaluate the migration of the chemicals and materials into the environment, the migration of the chemicals and materials that may reach humans during the end of life phase, and also assess the migration of the chemicals and materials that might be released to the environment during the end of life phase. With all of this, we would also propose actions to mitigate the impacts. For the case of the chemical A, with all the studies performed, we can conclude that for the human exposure, the level is 3, and for the environmental exposure, the level is 3 also. It means that it's between 50 and 25. Yes. And for the chemical B, we performed the same test, and we can conclude that the human exposure is level 2, and the environmental exposure is level 1. So if we repeat again and we do the SSbD score for this step, we can conclude that chemical A is obtain a better result than the chemical B. So at the end, we have obtained these results for each step, and as we need to carry out the step 4, but in this case, all the numbers makes us think that the best chemical would be the A, so we could replace the chemical B used currently for the chemical A. And this is our to remark that we need to do all the steps to obtain the final score.
Thank you, Paul. I think also now the attendees have a better overview what in practical we do, and we can open the floor to question and answer. We have around 15 minutes, so we have ample space for this. I know that there were already some questions from the attendance. Let's wait one moment, and then maybe I can break the ice with some questions to our speakers. Okay, we have Alessandro and then Miguel. So I will allow you to make the question. Allow camera. So first we go with Alessandro. Please, you can go ahead with your question.
Thank you. So first of all, thank you all the speakers for the amazing presentations. I have some questions for Ivana. First of all, why you choose spray coating? There is a particular reason for that?
Yes, basically, since our topic deals with thermoplastic, very thermally sensitive materials like PHA, for example, to start from there, we would like to explore the kind of a novel application in the field of paper industry, which is spray. We are fully aware that state of the art at this moment, continuous process is extrusion coating in a paper industry, and basically at later stage in the project, all good performing formulations in respect to the functionalities, but also in respect to the safety assessment will be evaluated for the extrusion coating in respect to the scale up, which we do expect some basically small modification, further modification on the formulation side, particularly when it comes to combining the polyhydroxyalkanoate with some lignin modified types in respect to the processing temperature. Because for spray, as you can see, we expose the material basically very short, if I may say so. In the case of lignin, we have a 60 seconds in a hot pressing, which is rather short compared to extrusion time, for example, once you go to extrusion coating process. And that was basically the main motivation. Since this is a low TRL project, BIO-SUSHY starts at TRL 3 at the beginning, and the final technology readiness level target is 5. But again, since we do have in our advisory board some partners actively involved and working in the field of paper, therefore we already discussed about the scaling up and validation of such materials for the other technologies.
Thank you. And the second one was about the choice of lignin. So what about that?
Yes, basically, yeah, we saw the target is 80% of bio-based. Yeah, it's true that for some PBS types, we can have not 100% of bio-based content. For some grades, we can have it, which is a bit different considering PHA, they're 100% bio-based polymers. And in terms of to further modify it, by additives, we like to stick to natural polymers like lignin is, and to explore the functionalities basically further of lignin, starting from spray application, because we saw many projects working in this field. But when it comes to safety assessment, there is still not too much things published when it comes to paper application, basically focusing on lignin. Therefore, we expect a nice outcome from not only from this technical side, but also on the SSbD assessment and framework, that we can really provide a bit more information for the complete research community and the industry a bit more on this safety assessment and sustainability assessment.
I was just curious because I know craft lignin, so craft lignin doesn't smell super good. So how you solve the problem of odor on the packaging? Because at the end, if your customer is taking the packaging and it smells badly, then it's not a good point to sell.
Basically, in this organic powder coatings, in that task, the percentage weight content of lignin, once it is being modified with thermoplastic materials, is very low. And this is basically what you just asked, that this potential odor of such components, if I may say so, would be basically reduced once we do not have very, very high content of lignin inside. But once again, since this is a bit not close to the market application, and we basically in this project would be happy to cover a lot information on the safety assessment and how basically different methodologies and approaches we can combine different natural polymers for the coating applications.
And sorry, I don't want to monopolize the discussion, but I was also curious about the color. So do you already have some perception of the customer about the color?
Basically, there is additional task in BIO-SUSHY where we talk a lot to our consumers and potential customers of such novel solutions for the paper and food packaging. And basically, when it comes to color, since our substrate, yes, indeed, it's a white one. At this moment, it's one type of a paper suitable for hot forming. And indeed, once we have a lignin inside, even with small weight content inside of thermoplastic material, color is becoming a bit more beige. But still not that brownish for the final. So when it comes to color, it will come later on in the project, that consumer perspective. At the moment, we are working on this a lot on this social also aspects when it comes to different value chains, because we cannot say at this moment too much on this, but yeah, pretty soon, beginning of next year, we will have more information on this consumer perspective. But indeed, yes, it is fully covered from another set aside, so from another partner within BIO-SUSHY working group.
Thank you. So very last point, because I work for Bloom Biorenewables, we are expert in biomass fractionation, and our lignin, it's already functionalized. It has a very light color in comparison to other, so craft it's super dark, if you can say. And our lignin also has no sulfur inside, so no smell. And if you are interested, we can get in touch. Maybe interesting for you to test it.
Definitely, because as you can see, we do have involved in our value chain end user, which is Ecosema. So we would be very happy to establish, definitely new contacts. So maybe I will put in a chat my contact email address. That it's easier for you, to make a first contact to us. So definitely that we are interested to explore more on a different types of lignin. Thank you.
Thank you.
Thank you, Alessandro. And now I will give the floor to Miguel. Also, Miguel, if you maybe can say a few words about, Alessandro didn't at the end, did. If you can say a few words about your entity, what's your background, and then you're free to make your question. Thank you.
Good morning, and thank you very much for the presentation and getting into the details, which I really appreciate. I'm an environmental and energy engineer. I worked for several entities in the public and private industry. And currently, I work for the Technological Center of Beta, a research center in the University of Leeds. And we have several projects. We particularly joined this meeting because of BioBond. We are working within a consortium in which lignin is one of the key value products. And those would be my questions, and others like NovaFert, etc., like bio-based fertilizers and many others, and yet to come. And yeah, we'll start using the safe and sustainable by design framework pretty often in the coming months. So my questions were like getting from the more punctual or more technical ones, and then broadening a bit more the topic. I guess that this is for Pau, but it's open for any speaker in general. So I won't address any of the speakers for the questions. So how do you define relevance in terms of measuring toxicity? Because you mentioned that concept but how do you really address relevance in terms of quantifying that? I guess that for the SSbD, it's pretty complicated in general, like to bring down to earth qualitative aspects into quantitative, but this is pretty interesting in terms of like how do you compare that, for example, like with cutoff or allocation criteria, etc. And the other question, the second one we could say, it's what's the sourcing of the raw lignin that you're functionalizing, which kind of wood or forest or the origin, if it's possible to specify a bit, or if you plan to, well, a bit about that. And about the testing of the SSbD framework itself, I guess that you're pretty aware that the European Commission is still in the last stage of an open consultation. If SUSHY project, BIO-SUSHY project itself, participating or planning to share some of the takeaways to really influence, because it's pretty interesting what you shared already. And in general, like about the material, like how much of this material will be plainly available in the website. I guess that since it's a European project, a lot of that, but many of the technical aspects were already shared by AXIA might not be. So I would like to know a bit more of that, because in terms of the technical details or mechanical properties or regarding water, that really makes a difference in terms of, for example, LCS speaking in a functional unit. I'm sorry for speaking that fast. I can reformulate any questions. So just feel free to make me to demand any clarification.
I would like to ask if you could repeat the first question.
Yeah, sorry. You mentioned the concept relevance when measuring toxicity. But for me, it's a bit difficult, and I guess that this is a discussion that we are having, not only the say practitioners, but when we get hands on the SSbD framework, how we quantify certain aspects, and relevance is one of these, and relevance for measuring toxicity, it's especially important. So I don't know if you have like any example, because or any slide that you can cling on to better support this idea, or maybe we can just brainstorm about this, because for me it's a bit blurry. It's like it's something that it's still not clear.
Good question.
No, I ask questions that normally are not written anywhere, so that's why.
For us, when an SSbD project is formulated, we need to think that, first of all, which endpoints or endpoints that we think that they are most relevant. Depends on, for example, the case study. If in the case of the case study that Ivana has presented, we thought that the dermal route, the digestion route, and I think that I forgot any one of these routes, but we think that these are the most relevant. So with these thoughts, we define which test could be the most interesting. Of course, we are not able to perform all the hazards or all the tests that the SSbD framework proposed, but we try to choose the best test that could fit for obtain the visual profile, the toxicity profile, or the impact that can be produced by this product. But I don't know if I answer your question with this.
I mean, there is not good answer or good question with this. It's just, I guess, that we are brainstorming, and we already know here that this framework, it's still open, it's not fixed. So that's precisely, they don't even know with detail how to do this, and it's very time consuming. So we have to cherry pick the tests that we perform, and based on that to generate extract the right parameters to not to waste too much time, because it's very time consuming yet. And I guess that the customers yet don't appreciate that. It is chemical sustainability strategy. It's going to take a while until customers really know what's behind. So yeah, but that's an answer. Thank you very much, Paul.
Yeah, so for University of Leeds, as I mentioned, that we are assessing the membrane interactions. So for, if I understand your question right, for quantitative relevance, I showed that we are using the different weights, Langmuir, adsorption, isotherm, and dose response. So by fitting those the data to different weights, we calculate the limit of detection actually. So that limit of detection can tell us like whether to go beyond that amount or not. And similarly, in the leachates, we have a plan to quantitatively analyze those leachate with the LC-MS-MS technique, and to see how much of the lignin is leached into the solution, into the leachate. Because anyway, like if anything material is leaching into, like coating is not stable, so there's no point to use that. And yeah, so we can quantitatively and qualitatively both, we have a plan next to measure those materials into the leachate. I think Andrew want to say something, or Andrew have a question?
No, I wanted to make a comment. I'm writing in the chat, but thank you, Ashley, brilliant. It's just that toxicity is a very general concept and includes many things. And colleagues I know in Finland, MISFIC, they express what's called a tox score, which is a combination of 5 different very diverse endpoints. But in Leeds, the biomembrane sensor is a pre-screener. It's not an ultimate screener, it's a pre-screener, a kind of triage. And you can select materials from the pre-screener for more extensive measurements. So we're only good at Leeds if we're working with, as we are here with ITENE, other people who do more, who do in vitro tests. But the biomembrane sensor is directly related to cytotoxicity, but is very, very much more sensitive. And that's why using the normal in vitro test, you may not detect the cytotoxicity, although we can detect it because we're extremely sensitive. Okay. Thank you.
Thank you, Andrew. Thank you, Paolo, Ashi, and Lotsonia. Yes.
Sorry to interrupt.
No problem. I think we have time. Yes.
It was a very interesting concept and a very, very interesting question that this gentleman raised. I had to say something. Sorry.
No, thank you very much. I'm just curious because I launched 4 questions and we could only address one, but I would really appreciate if we can just briefly talk about the second one, which is the sourcing of the lignin that you're getting so far. Is it obtained at lab scale? Is it obtained within a pilot scale facility, an industry? How do you obtain it for then functionalize it? I think you're muted, Pau, if you're talking.
No, I was thinking that I thought the question would be more for Ivana because it's related to the lignin and so on.
Can you just, for myself, just summarize a bit because the introduction of you and speech was a bit longer. So when it comes to lignin, why it has been selected here, or
no, not selected lignin as because of the properties itself, but the sourcing, like where does it come from, which process, or in general, just the provider that you're using? Because I'm very curious because lignin so far, the estimated annual growth is very important, but it's still the industrial development of this substance still quite low. So in the bio-based industry, it's very interesting to understand between us, how are we doing? Because we know within the project of Biobond that interesting things are moving on, but BIO-SUSHY.
Okay. Basically, when it comes to production, so to say, of specific components being used in our formulation development, we do in parallel life cycle assessments. So when it comes to any inputs in terms of the way different materials are here being produced in more sustainable or not that much sustainable way, that all that points are basically covered under life cycle assessment. So that's also a part of this project in a separated task that runs really in parallel with all our R&D technical activities. So basically, we are guided from the beginning on in respect to, as I said, different impacts on the sustainability, how we can basically go and develop further BIO-SUSHY coatings in here. So it is fully supported by that, evaluating that sustainability step. In parallel, yes, as commented, because we heard also a question from Blue Renewables, we are very open to explore, as I'm fully aware that there are different steps basically providing more functionalized lignin, basically to produce it. So we are fully open to explore the different types of lignin here and to compare, so not only the functionalities, but also the way they're being produced. And that part is fully linked to the life cycle assessment in here. So yes, such a topic is covered under BIO-SUSHY. And yeah, sometimes it's not easy. One, I need to admit, because very often life cycle assessment people, working group, is really having a problem getting all inputs on the production itself. So very often we need to take care of some assumptions and collecting the data from the literature, because once you do not have a company directly involved in the project, it's not the easiest way to say it open to get all needed data for accurate life cycle assessment. And that might be true always, yeah, unfortunately for the bio-based materials, because this is something that still has to be improved by synchronizing different methodologies, I believe, when it comes to LCA assessment in general.
Thank you very much, Ivana, because that's absolutely key for any kind of these bio-based projects that rely on lignin. Thanks.
Very well.
Thank you. Thank you. I think we are on time to close. I know that there are maybe other questions. They're also responding in the chat, but you can still reach out to us by email or with the email from the partners. So I would like to conclude this training session by thanking first our speakers that did an excellent job. They put a lot of effort in delivering this presentation. Thank you, Paul, for providing us a very comprehensive overview of what is SSbD and also for the practical example. Thank you, Ivana, for your valuable input on the technical part and on the lignin. Thank you, Ashi, for the very insightful presentation more on the chemistry part, on the functional lignin and the biomembrane sensor. And thanks to our speakers. I think we were about 30-40 people. So thank you very much. Here I can leave you the contact for reaching out to us and also to follow us. And I hope that especially for the speakers, we tried for the participant, we tried to develop presentation that suited your expertise, and you could get some insight, some actionable insight that you can apply in your SSbD practices. And with this, I would like to conclude and reminding you that all slides will be sent to you, also the recording. And thank you very much.